start out just by talking a little bit about me and what I do. So I lead a team of people, and we do a couple of things. So the Aerospace Technology Institute sets the aerospace technology strategy for the UK, and we work with the government to do funding of aerospace technology research. We've recently had the government extend our funding agreement out to 2035, and that's worth a couple of billion in terms of overall value. But as we might talk about later on, actually in aerospace terms, that's not a huge amount of money. What it means, though, is we can start those technologies on their journey, and then when they're ready, when they're at technology readiness level 6, so you've proven them in a representative environment, then that's when they can be taken on by private investment. The second thing that I and my team do is analysis for what different technologies mean at aircraft level and different levels in addition to that. And that's what we're going to talk about today. So if I share my screen, let's go for that. Janine, can you see that okay?
Yeah, perfect.
Perfect. Okay. So the title of the webinar tonight is Pushing the Boundaries of Aerospace Technology. And hopefully, as I've explained about what the ATI do, you will understand why that's something that's both dear to me and also relevant to my job role. The first thing, if this is going to go on, the first thing that we need to understand about aviation is that it's a global system. So what's showing on the screen at the moment is all the different flights in a day all around the world. When you look at the number of flights that go all around the world in that day, it is very clear that you cannot just consider one part of the system. You have to have something that addresses all of the different requirements. And so typically, the way we do that in the ATI is we think about it in a few different ways. So first of all, we start with aircraft models, and those could be existing aircraft, or they could be future aircraft. The TLARs, so on the left-hand side, that stands for top-level aircraft requirements. And we'll come back to those in later slides. But those are things like how many people, how far, how fast does the aircraft fly, things like that. And that generates aircraft capability. And that typically is how many people and how far can it go. And then we use fleet models or market models. And that gives us a number of aircraft in the overall global fleet. And this is important for a number of reasons. The first is when you introduce a new aircraft, it doesn't immediately take over from the aircraft that are flying today. It takes a number of years for that aircraft to roll into the fleet, is the term we use. And so over time, those new aircraft will take over market share. And that's where you then get into the sustainability model. So if they burn less fuel, that's good, but it will take time for that new aircraft to roll through the fleet. And you have to factor that in when you're looking at what the overall sustainability impact is. We typically have a number of market scenarios where aircraft come in earlier or later or have different capability to look at the sensitivity to that. And this is ultimately back to my original point of you have to consider the global aviation system. The final thing is then the performance and emissions data from the aircraft models feed into the sustainability model. And that then gives you the fuel burn per aircraft, and you can convert fuel burn to CO2 emissions as a direct proportion, and it's about 3.6 kilograms of carbon for every kilogram of kerosene burned. And that allows you to then to assess the total emissions. And at the end of the webinar today, I'll show you some publicly available tools where you can do some of this analysis yourself and have a go. So let's step through some of those things. So the ATI have a number of what we call reference aircraft. What we've done with these aircraft is say, what could the next generation of aircraft look like, both in terms of performance and the technologies that would drive them? So these aircraft, the one on the right is a single aisle, so an A320 or 737 type aircraft, and the one on the left is a wide body or twin aisle, so that could be an A350, a 787 or a 777. These are ATI designed aircraft that won't ever go into production. That's not what they're for. They're study aircraft so that we can look at the impact of different things. So to continue that example, I'm going to look at the single aisle future aircraft model in a little bit more detail. So let's look at what those top level aircraft requirements are. And I've put some of them on the right hand side. So the maximum range that we designed for is 3,450 nautical miles. That's about a third of the way around the world. But in practice, you may have headwinds, so that takes away from how far you can fly. If you have lots of weight on board or payload, you may be able to fly less far, or you have a volume limit with your fuel tanks that can also limit how far you can fly. I'm going to jump for a second to the passengers number. So we assume 160 passengers, but that also depends on how much space you need between the seats, because that drives how long your fuselage is. But the number of passengers or payload and the distance that you can carry that payload or the number of passengers is a key factor in how the aircraft makes money for an airline. Ultimately, that's what the aircraft is there to do, to transport some payload over a distance. The more efficiently it can do that, the better it is for the airline. And ultimately, the airline in this case is the end customer. The diversion and contingency, we follow some typical rules. So a diversion is where you were aiming for a particular airport, let's say London Heathrow, and there is some reason that you can't land at Heathrow, whether it's weather, whether it's closed for any reason like an accident or an incident, and you have to divert to another airport. There are pretty standard rules for what you assume in that case. In this case, it's 200 nautical miles, so that's almost all the way to Paris, but certainly to some other major UK airports. And when you get there, you would have to assume that you fly around for 30 minutes, and then you also have trip fuel contingency. And the trip fuel is the amount of fuel for the trip, and you add a percentage. And in a similar way, the captain of any aircraft you fly on will have to make his own decision about carrying extra fuel. So we make an assumption about that when we do aircraft design to ensure that that's factored in. The cruise Mach number is how fast the aircraft flies in the cruise phase. Mach number is a ratio relative to the speed of sound. So the speed of sound is Mach 1. So in this case, at 0.78, we are slightly below the speed of sound. We are on the verge of what we would know as what's known as the transonic region. Single aisle aircraft today tend to cruise or be designed to cruise at about this level, and wide body aircraft cruise a bit further. The next number is the takeoff field length. So that is how much runway do you need to operate this aircraft? And that gives you a restriction on the airports that this aircraft can operate within. The approach speed is the next interesting one. That is, how fast does the aircraft fly when it's coming into land? For most aircraft designs, but not all, the wing is sized by the approach speed, because that is when you need the maximum lift at the lowest speed. We call this the CL usable max. That means the maximum lift coefficient that you can use, not necessarily what the wing can generate, but that you can actually achieve in flight conditions. at the max landing weight. And this is an interesting thing in itself, because aircraft design is a circular activity. And what I mean by that is the aircraft has to carry its own weight. So if I make my wing bigger, then it also weighs more. And that means I need more lift. So maybe I then need a bigger wing again. But because my wing is now heavier, I need more thrust. So I might need a bigger engine as well. But then my engine also weighs more. So then I need more lift and more thrust. And what this means when you make a change to an aircraft design is you have to iterate around the solution. So what this means is you keep running the equations again and again and again until they converge on a single answer. And what that means is that a relatively small change can have a big impact. Or to put it another way, changing one thing on an aircraft can also affect many other things. The maximum structural payload is a limitation that you get for how much weight the aircraft can carry in passengers or cargo relative to the structural limits on things like the wings. The next few are operational requirements. So initial climb altitude, these are defined here in flight levels, but that's an operational term. So flight level 350 is equivalent to 35,000 feet. You also have to define things like the temperatures that you're doing that at. So in this case, it's ISA plus 15. ISA is the International Standard Atmosphere because the local temperature and pressure affect how much thrust you can get out of your engine and how much lift you can generate with your wing. And you also have to specify how heavy the aircraft is at that point. So in this case, we've specified at the maximum takeoff weight. The time and the distance to that initial climb altitude are also important. If we have any budding pilots on the call, you'll know that there are different climb ratings that you can choose to fly. You can choose to fly minimum time to altitude or minimum distance. And depending on the aircraft, those things can be quite different. And finally, we consider the ICAO Aerodrome Reference Code. What that gives you is a box which the aircraft has to fit within on the ground. And in this case, it's called a code C. So that means the wingspan on the ground is less than 36 meters, and the outer main gear wheel span is less than 9 meters. Some recent aircraft, like the 777X, have got round this wingspan on the ground versus in flight question by having folding wingtips. So that reduces the wingspan on the ground relative to what you would see in flight. So that's our starting point. We've decided that this is what our aircraft needs to deliver. So the question then is, what technologies are we looking at to include on this aircraft? In this case, the ATI is investing in a wide range of technologies. The biggest one I'd like to talk about here is what we call a high aspect ratio wing. In simple terms, that means the wing is a high span and thin wing. That means that you can fly more efficiently, but it also brings challenges in the structure because as the wing gets longer and thinner, it's harder for the structure to resist the bending moment and how much it bends for a given set of material properties. And that then changes how much the wing weighs. And like most things on an aircraft, what you find is that there is an optimum value of something where everything balances, and then it gets worse again. And I'll show you an example of this relating to propulsion in a second. The other thing that you have to consider, or one of the other things you have to consider, is what the aircraft is made from. Traditionally, aircraft tended to be metallic structures, but increasingly we're seeing the use of composites. That can have benefits for lightness and other things like fatigue properties, but it can introduce challenges for rate of manufacture. which is how many of a particular component or system or structure you can produce in a day or a week or a month. Typically today, manufacturers aim for a production rate of a single-aisle aircraft of around 70 per month is the target. What's achieved at the moment is between 30 and 50, depending on the manufacturer. Longer term, the technologies that we're looking at could get us to potentially 100 aircraft a month. If you look at that from an engine perspective, then that, because there are 2 engines on each aircraft, would be 200 engines a month, which is, in aerospace terms, a lot. If you're a fan of cars, you might think that that's not very many, but believe me when I say, in large aircraft terms, that is a very high number. The other technologies that we look at are advanced systems. So on the aircraft, you have systems to provide control surface movements and control the aircraft, provide feedback to the pilots, provide air into the cabin, and pressurize when at altitude. These are just examples of safety critical systems that we are constantly trying to improve in terms of capability, robustness, size, weight, and cost. You can't necessarily see those things from the outside of the aircraft. So this aircraft might look very similar to what you see flying today, but under the skin, we've made assumptions for a whole suite of different technologies. What I'd like to do now is dive into a specific example around some of the complexities of the propulsion system. And for the single-aisle aircraft I showed on the last slide, that means a gas turbine or a jet engine. One of the things that is a constant driver in aerospace is the drive to make it more fuel efficient. Usually for a jet engine, this is called SFC, specific fuel consumption. What that means is you divide the efficiency by the thrust and normalize it. That allows you to compare engines of different size and thrust classes on a constant metric. There have been a range of ways that the efficiency has increased in gas turbines in the last 10, 15, 20 years. The predominant one is to increase what's known as the bypass ratio. The bypass ratio is the ratio of air that goes just through the fan versus the air that goes through the fan and the core of the engine. So the core of the engine is what you can see in the middle of the picture behind my graph, and the fan is what sits at the front of the engine. Today's engines are between 8 and 10, depending on the engine that you're talking about in service. We have done studies on engines up to about 18 bypass ratio. And this is where you get an interesting example of what I was talking about before. If you just look at the engine efficiency, as you increase the bypass ratio, the engine continues to get more and more efficient. That's what the bottom line on my graph shows. However, when you put that onto the aircraft and you have to consider what we would call the integration of that engine or propulsion system, you start having to consider other factors. Because the bypass ratio increases, the engine gets bigger, the diameter of the engine increases. What that means is the engine weighs more. And at aircraft level, as we talked about before, if you need more weight, that will have a spiral effect on the size of the wing and the thrust you need, and it will cycle round and round. And what that means is you get an optimum point, but if you push it too far, it gets worse again. But that's not all of the story, because then you also have to consider that the nacelle diameter has got bigger, so that means you get more drag, more aerodynamic drag. So that also gives you a further detriment. So what that means is the black line shows where the optimum is at aircraft level, because it balances out all of those things of SFC and weight and drag. And this is a constant theme if you are an aircraft designer, having to balance all of these different elements to try and find an optimum. Aircraft design is not a deterministic discipline. What that means is there is no single right answer. What you are trying to do is optimize a competing set of requirements and technologies to give different solutions for different markets. What you can then do is think about, how do I change the engine? So everything I've just been describing is for a ducted engine. The principles still apply for other configurations. So some of you may be aware that open rotor or unducted fan or unducted fan is a design that's currently being studied in the market. This engine or concept is known as the CFM Rise. CFM is an engine company. This engine has no nacelle, has no duct around the fan. What that means is you help some of the effects that we were just discussing. So my bypass ratio goes up dramatically, but I don't have the same increase in weight because I don't have that big nacelle that goes around the outside. It's slightly different to a propeller because you have, in this case, a rotating fan at the front, and on the white engine casing, a row of stators. That means those vanes are static, they don't rotate. Both of those stages are variable pitch, which means they rotate relative to the airflow. And this is one of the ideas and one of the technologies that people are investigating to further improve the efficiency of gas turbines. The flip side of that is that the diameter of that propeller is significantly bigger than an existing ducted gas turbine. So that means you have to consider different aircraft configurations, and that then brings different challenges. So today, most aircraft have what we would call a low wing, where the wing joins into the bottom of the fuselage. However, if you try that with an open rotor configuration, you don't have enough ground clearance for the fan in terms of height off the ground. So shown here are some possible ways which you could overcome that problem. The top left shows what's known as a high wing. So that means the wing moves to the top of the fuselage, but that brings different challenges. You have to go to what's known as a T-tail. So the horizontal stabilizer at the rear of the aircraft moves to the top of the vertical fin. You have to raise the wing above the cabin. Otherwise, you would have a restriction in the aircraft where the wing encroaches into the cabin. And some of you may have flown on aircraft where that actually happens. And in some older aircraft, the overhead lockers under the wing are very small. They're known as briefcase holders. The bottom picture here is what's known as a gull wing. So a gull wing is where the wing starts at the bottom, but curves upwards as it goes away from the fuselage. That is another potential configuration, but brings its own challenges because the wing is then curved, and that then introduces different load conditions and different challenges with how that structure is integrated into the bottom of the aircraft. And of course, it gives you less ground clearance than the high wing. So you have two options. You go for a smaller fan, or you extend the length of your undercarriage. Again, those things have different pros and cons on the design. Another solution could be to go for what we call fuselage mounted engines, shown in the top right, where they're at the rear of the aircraft. That has some benefits because the wing is then a clean wing with no engines on, which means you could get some benefit from that. But it also has some downsides. One of the key things with aircraft design is the center of mass and the center of lift. The center of mass is also the center of gravity. So some of you may be familiar with that concept. It's where you could balance a shape on a single point and it would stay balanced. The center of lift is the opposite. It's where it's an invisible point where the lift could be imagined to act through the aircraft. But if you move the engines to the back of the aircraft, that has the effect of moving that center of gravity or center of mass backwards. Because there are very important relationships between where you need the center of mass to be relative to the center of lift, that also means you have to move the wing backwards. But because you're then moving the wing backwards as well, that has the effect of moving the center of gravity even further back. If you move your wing backwards, you also have less distance between the wing and the tail. And that's an important parameter or a moment arm for how effective your tail surface is. So typically you have to increase the size of your tail surface. If you increase the size of your tail surface, it weighs more, and then you get back into that loop that I talked about. One of the other ways that this is a good example of what happens if an aircraft designer gets it wrong. This is a genuine picture of an aircraft where the weight and balance has gone outside of limits. The center of gravity has shifted far enough behind the main landing gear that the aircraft has tipped up on its tail. Some older aircraft had to have struts to prevent this from happening, but as you can appreciate, this is not something that airlines are keen to happen in service, because not only does it damage the aircraft, it is also very dangerous. So what I'd like to talk about now is moving on to some other future aircraft concepts that I've also worked on. This was part of the FlyZero project. The FlyZero project was a team of about 100 people for a year, and our aim was to examine the possibility for zero carbon aviation and what the different options could be. Shown in this picture are 3 concepts that we came up with for different hydrogen-powered aircraft. I know some of the other webinars have talked about electric-powered aircraft, and today I'm going to focus on hydrogen-powered aircraft. In my view, hydrogen is the most promising zero-carbon fuel for large aircraft. The main reason for that is because batteries are not currently good enough to scale up to large aircraft, and it's extremely uncertain when they will be good enough. I think we need to be investigating what those aircraft could look like now. And that was ultimately the conclusion of the FlyZero project. So when you start, as an aircraft designer, when you start something like this with a blank sheet of paper and you say, what options could we have for aircraft configuration with hydrogen propulsion? You come up with lots of different ideas. These are some of the different ideas that we came up with as a team. And at that initial ideas phase, it's not about discounting things. You come up with all of the possible combinations, and then you work through different analyses to pare those down for different reasons. Some of that could be the requirements. Some of it could be some limitations around aircraft tipping. In the case of hydrogen, it's often because the volume of the fuel is much more than kerosene. Hydrogen is a very interesting fuel. It's much lighter than kerosene for the same amount of energy, but it occupies a much bigger volume. As a gas, you can compress it to reduce that volume, or you can make it a liquid. If you choose to make it a liquid, it means you have to store it at minus 253 degrees Celsius. That's about 20 degrees above absolute zero, but it's extremely cold. What that means is that you have a real challenge with how you keep that fuel very cold through the flight and the time on the ground for an aircraft. What we eventually did, having done all of those different analyses and looked at the options, is narrow it down to 3 final concepts. A regional concept, which is hydrogen electric propulsion, so using fuel cells, and the narrow body and the mid-size concepts, which were directly burning hydrogen in a gas turbine. What I'd like to do now is take you through the mid-size concept in a little bit more detail and explain some of the considerations that we had to think about when we were adapting an aircraft to be powered by hydrogen. The first is, as I said, the fuel itself. Because you want to keep the fuel so cold, you have to have lots of insulation around the tank. In practice, what that means is it's not sensible to store the fuel in the wing. So then you have to say, where else could I put the fuel? Some of the concepts on the previous slide, on the different ideas slide, had hydrogen tanks above the cabin, below the cabin, in separate pods. We looked at all sorts of different options. What we ultimately decided to do is put a big hydrogen tank at the rear of the aircraft, because if the fuel is not going in the wing, it's not necessarily an easier answer, but what we've chosen to do here is put it inside the fuselage. We have also increased the fuselage diameter of the aircraft, and that gives us more diameter and more volume on that hydrogen tank. This aircraft was designed to fly over 5,000 nautical miles, or approximately the distance between London and Hong Kong, because we wanted to show that we thought whether a hydrogen aircraft could fly long range. But then we had to consider the weight and balance of the aircraft. For safety reasons, you have to have more than one hydrogen tank, but it's less space efficient to put both of those hydrogen tanks at the rear of the aircraft. If you have too many tanks at the rear of the aircraft tips over on its tail. What we've had to do is move some of the hydrogen tanks forward in front of the undercarriage. Most aircraft today have a cutout in the pressure vessel in the fuselage, in a lot of cases so that the landing gear can fold up into that gap. They have a supporting structure called a keel beam that sits between the wheels of the undercarriage when it's folded to provide structural reinforcement. What we've done here is extended that fuselage cutout, extended that keel beam, and then put two hydrogen tanks outside of the pressure vessel, either side of that keel beam. What that enables us to do is to manage the center of gravity and the center of mass and how they move as you burn that fuel to stay within reasonable limits for the aircraft to give acceptable performance. The hydrogen gas turbine is another interesting area. Hydrogen is a very different fuel to kerosene. If anything, the difficulty is stopping it burning rather than starting it burning. The flame speed, so how quickly the flame travels when it's on fire, is much higher. So you have to think about what that means for your combustor design. You also have to think about what that means for your turbine. The hot gases coming out of the back of the combustor in an engine today are typically hotter than the melting point of the metal that the turbine is made from. That means you have to be very careful in how you design the turbine and the cooling and the airflow that goes with it to make sure that the turbine gives you maximum performance but doesn't melt. You also then have a question around how you get the hydrogen from the fuel tank to the engines. Today, kerosene stays as a liquid all the way through that fuel system just until the point when it's burned in the combustor. With hydrogen in a liquid form, you cannot put the liquid hydrogen into the combustor because it's too cold. What you have to do is turn it into a gas by adding heat to it. But that adds complexity to the system as you're going through the aircraft. What you then have to do is make sure that the hydrogen doesn't leak. And if it does, that doesn't become dangerous. Hydrogen is a very different fuel to kerosene in this regard as well, because you need very small amounts of hydrogen to leak before it can become an explosive atmosphere. those are some of the really important considerations that we had to think about when designing this aircraft. In addition to that, you then have to have different systems. How do we monitor for hydrogen leaks? How do we understand how much fuel is left in a hydrogen tank? Because it's so cold, you can't typically use existing systems where you would use for kerosene. Hydrogen pumps and valves typically exist today, but they're designed for space rockets, and typically they're only built to last for 7 to 10 hours, whereas an aircraft would need those pumps to last for hundreds of thousands of hours. I hope that gives you an indication of the scale of the technical challenge that it will take to make a hydrogen aircraft work. But ultimately, solving those engineering challenges are what good engineers are there to do. And that is one of the biggest reasons that I love being an aerospace engineer. So the final thing I'm going to talk about, hopefully I've given you a bit of inspiration for the kind of things that you need to think about when you're doing the innovation challenge. It's great to come up with a new idea, but what I'm going to be looking for is for you to think about, what does that mean when I put it onto an aircraft? What can my aircraft do? What will the different bits of the aircraft need to, how will they need to change, and what will that mean? So what I'm going to talk about now are some publicly available tools that you might be able to use to help with that design. To be clear, these are potentially difficult tools to use. It depends on how old you are and where you are in your education. But these tools have been used by professional engineers, but some of them are also accessible to people much earlier in their education. So OpenVSP is a geometry tool with other analyses that you can do. It's a free, and these tools are all free. OpenFoam is a CFD tool. So CFD is essentially computational aerodynamics. So it enables you to look at the aerodynamics of an aircraft on a computer and think about what's going on with lift and drag and different things. The ATI toolkit is where you can find the reference models that I talked about earlier, and you can download the spec and the detailed parameters for what that aircraft does and its dimensions and everything you would need to try and recreate that model in whatever toolkit you want. Finally, I'd like to talk about the Boeing Cascade tool. So this is, again, a free-to-use tool online. Anybody can register for this. What it enables you to do is look at different scenarios for how aviation might decarbonize. You can look at different fuels, such as hydrogen or SAF or other things. You can look at different types of aircraft when they come into the market. You can look at different fuel impacts. So if I have SAF, there are different types of SAF. They have different sustainability benefits. And this is a professional grade tool that Boeing have made available to the general public because they recognize the importance of everybody understanding what the opportunities are to decarbonize aviation, but also the scale of the challenge. On the right-hand side of the slide, you can see a typical plot as an example of what Cascade can do. I'm going to touch on this briefly, but I would genuinely encourage you to go and play with the tool. There are tutorials online for free to help you understand all of the different things. What this shows, if you take the top line, is aviation traffic. The number of passengers is expected to grow in the coming years. That means if nothing else changes, emissions from aviation will continue to grow. What you then have to do is say, well, I can change different things. I can change how efficient my aircraft are, or I could change the amount of SAF that's available, or I could change how I route my aircraft through the sky to make them more efficient. And just an example, the tool will then give you, through the color coding, how much CO2 over time, that change, be it a new aircraft or a new fuel, will offset in terms of the emissions. With the clear target, although it's a very challenging one, to get all the way down to zero. So as I say, I would really encourage you to go and play with these tools. Ask different people that you know that have experience of these kind of things to help you learn and help you understand what those challenges are. So with that, I'm conscious that I wanted to leave some time for questions. So I'm going to stop sharing my screen. And I haven't been monitoring the chat, so I don't know if we've had any questions. So I'm happy for people either to raise questions directly by coming off mute or putting them in the chat. But I hope you found that an interesting talk.
Yeah, just checking. There wasn't anything in the chat question-wise just yet. But yeah, please feel free to add your questions, guys. Anybody? No, don't think there are any today. Oh, yep, there we go. Ethan, yep. Hi, Ethan.
Hi. I just wanted to ask what are the next steps really? Looking into the future, obviously the designs that you were talking about were really, really interesting, and I was, wanting to ask what came of them really.
Good question. It's actually an iterative process. The designs I was describing are continuously evolving as we get new information about different technologies. So whether it's the next generation of systems or another material or a way to make the wing even lighter, we're constantly evolving those models to understand what it means. Where it comes to a crunch point is ultimately when an aircraft manufacturer decides to make their next product. Now that's not something that the ATI do, but there are people in Airbus and Boeing and Embraer and Bombardier and all the aircraft manufacturers whose job is to do exactly the kind of analysis that I was outlining today and ultimately try and meet a target that they've set. I can't tell you what the exact target is that Airbus or Boeing have set themselves internally because they don't share that. But to give you an example, you would typically be looking for a minimum of 10, probably 15% improvement in the efficiency of your aircraft to justify the cost of launching that next product. To put it into context, for an aircraft to develop a new aircraft, you could be looking at anywhere between 10 and 15 billion dollars. So it's not something that people will do lightly. And it also means you have to make something that will go into service for a long time to make that money back. So that really is where it comes to the crunch. In terms of the market, the general consensus is that we would expect to see the next platform in the single aisle market and sometime in the mid to late 2030s. We don't know exactly when yet because it hasn't been launched, but so what I mean by that is between 2035 and 2040, and we don't know exactly when. That's the general consensus in terms of what people think.
Brilliant. Thank you very much.
You're very welcome.
So it looks like we're getting someone in the chat pop a question in, hopefully. But feel free to come off mute and ask as well, guys. Ashrith is just writing.
Just while that's...
Sorry.
Oh, go on.
Oh,
can you hear me? Sorry,
hello.
I found somewhere to pull over now, so I can come off mute. David, what do you think the timeline is for a completely carbon neutral global aircraft fleet? So we have all of these current aircraft in service at the moment, and you reckon a 10 or 15% decrease will make it viable for a new short-haul aircraft. So it seems to me like it's going to be many decades. What's your thoughts on that? Do you have your own feelings on approximately how long?
I can give you my thoughts. Just bear with me 1 second. Sorry, I just needed to turn something off in my office. So it ties into what I gave as the previous answer. The general consensus is the next generation of single-aisle aircraft will come sometime in the 2030s, in the second half of the decade. If you look at historical precedent, there's a minimum of 15 years between one new aircraft coming into service and then the replacement for that aircraft, because you have to allow time to make the money back that people have invested in that first aircraft. So to put that numerically, if you have a clean sheet kerosene or SAF powered aircraft in 2035, the next generation of aircraft we wouldn't expect until around 2050. All the evidence so far is that next generation of aircraft will be kerosene or SAF powered because of the risks involved. So that would suggest that the earliest you will see a hydrogen or zero carbon aircraft in that single aisle space would be around 2050. And those timescales could move in parallel. So if 2035 becomes 2040, you would expect the next aircraft to slip in the same by the same amount. So ultimately, any job like mine where you're predicting the future is extremely difficult to have certainty. But the way that I look at it is, if we want that next aircraft plus one to have any chance of being a zero carbon aircraft, we have to be investing in the technologies that enable that transition now, because aviation and aerospace are such long cycle businesses. Typically, it can take 10 to 20 years for technologies to make their way into products. And actually, if you look at it, between now and 2050, there's only 25 years. And to pick up on another thing you said, there's what I'm trying to show at the moment, or what the technology research that ATI is trying to show initially, is that a technology is feasible. What then has to happen to get something into service is that you have to show that it's practical. So as I say, that means it's one thing to be able to make a hydrogen aircraft fly, but to be able to make it do 5 flights a day, 340 days a year, for 10 years before you have to take the engines off, is a very different thing. And that ultimately is what takes the time to bring it through. Personally, I like to take an optimistic view, and I see my job as challenging the sector to say, how quickly can we bring in a zero carbon aircraft, and how quickly can we introduce other measures? So that could be contrail avoidance, it could be operational improvement, it could be increased SAF. Ultimately, we need to be trying to accelerate all of these different measures to come into service as quickly as we can. And I don't know the age of people on the call, but the innovation of people coming into the workforce and going through their education, these are the people, you are the people that will bring those new ideas into reality and into service and into products. And that, I think, is a really exciting thing. Just to come to Ashrit's question in the chat, how long have hydrogen-powered aircraft been explored in the industry, and how long do you think it will take to come into reality? Okay, so I think I've probably answered the second bit with my last answer. To answer the first bit, hydrogen-powered aircraft have been actually explored for a very long time. So some of you may have heard of a very famous aircraft designer called Kelly Johnson. He designed various aircraft in the sort of 1950s and in the US, including things like the SR-71, the U-2. They did a study in the 1950s on a hydrogen-powered aircraft because they could see the potential benefits because of the light weight of the fuel. At the time, the technology was not good enough to enable that aircraft to be a practical proposition. But that's the other thing where technology is so interesting, because as technology changes over time, as a designer, you have to constantly question yourself, how does that change what I can achieve with my aircraft design when previously things might not have been possible, but now they are because new technology has become available. The next question from Sasha. Since in the last years we've had an uprising of AI in different sectors, what plans do you think there are to implement it in aerospace and in what roles? That is a really good question. AI, like all tools, has its benefits and opportunities, but it also has its downsides. AI is very good at doing certain things. One of the challenges with most AI is that it will give you an answer, but it's difficult to know if you can trust it because it doesn't explain how it's arrived at that answer and what sources it has used. The way I think, certainly in the next 5, 10, 15 years, AI will be used in aerospace is in a supporting role to help designers quickly assess lots of different options. But I still think that it will ultimately remain with the human to make a final decision. And the reason for that is if you look at things like the certification rules, you cannot use AI when it's a black box to justify why something is safe to fly because you don't understand the reasoning that it has applied. That's still actually a very difficult thing for humans to do. And at the moment, we tend to rely on people with lots of experience to cover all the different bases. There are research programs looking at how you can make an AI system that is auditable and explains how it has reached a decision and how it has done analysis, but those are still in their infancy. And ultimately, for lots of other use cases, like writing software for phone apps and things like that, it's not a real driver in terms of growth. So it's quite a unique aspect to safety critical industries like aerospace, and it's a relatively small driver compared to some of those other things. So that's my view. Whether it will change, again, this is another thing. If one thing we do know is that AI is evolving incredibly fast. So maybe I'm underestimating when it will come in. The other area that AI is relevant is autonomous flight. So no crew, single crew, things like that. Again, a big challenge at the moment is that AI is not necessarily deterministic. You can give it the same set of inputs and it can come up with different answers for different reasons. And at the moment, that would be something that you couldn't certify because the safety regulations assume a deterministic system. If you do the same things, if you put the same things into the system, you always get the same outputs. And these are the kind of challenges that the industry are currently investigating.
Anyone else got any questions? No, I think we're good, I think. Well, David, thank you so much for taking the time this evening to obviously do the webinar. Very, very interesting. I hope everyone found that really useful. Our next one is next Thursday evening. So if you haven't registered, please go and take a look. But have a lovely evening wherever you are. And yeah, speak soon. Thank you, guys.
Thanks, guys.